Okay, so for this particular lecture, we're going to be looking at the periodic table. We'll also be looking at molecules, compounds, and formulas. And that'll be it for this lecture. Maybe it'll be a little shorter than the others. Okay, periodic table. Here you want to learn the terminology of the periodic table and how to use that information. And you want to recognize similarities and differences in properties of some of the common elements of a group. So let's look at the first slide here. Features of the periodic table. The periodic table is divided into what we call periods. Periods, horizontal rows. So that's kind of redundant. When I say horizontal, it is a row. There are 7 rows and also 7 periods. 1, 2, 3, 4, 5, 6, 7. Now, when I look at the periodic table, I think of it as like a castle. Here's a castle tower. Here's a castle tower. Here's a castle wall in the middle, and here's the castle moat. So you might be hearing me calling it the left tower, the right tower, the wall, and the moat, okay? So if we take a look here at the left tower, you can see that the numbers for the periods are in order from 1 through 7. Now, an interesting thing is when you look at the moat, these are parts of periods 6 and parts of period 7. If you look at period 6, you'll notice that the atomic number, I believe it's 57, jumps to 58 down here, and then comes back up to like 72 back up here. So this is actually part of period 7, and this part of the moat is part of period, excuse me, I said that wrong. This top part of the moat is part of period 6, and this bottom part of the moat is part of period 7. Okay, now when you look at the vertical assemblies of elements, we call those groups or families, okay? And so here, you want to know how to number the groups when it comes to the 2 towers. The groups are numbered as follows: 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, all in order. Don't worry about the B groups because it starts off with like 3B, 4B, 5B, 6B, 7B, 8B, 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 1B, 2B. And we never use that. So don't worry about the B groups, but these are the wall are the B groups. These guys down here are not really part of any group. Okay, so the groups are elements of similar properties. Okay, now a property of a substance is its formula. So if we take a look at the formula of all these 1As, when they combine with chlorine, it's always one of these and one chlorine, HCl, LiCl, and ACl. So they all have that same chemical property of combining with chlorine. Whereas if you look at 2A, it would be, let's see, BCl2 and MgCl2 and CaCl2. So they all combine in the same way with chlorine, where it's one of them and 2 of chlorines, similar properties. Now, you also want to know what the towers are, what the wall is, and what the moat is. The 2 towers are called the main groups. Now, these guys in here, the B groups, the wall, they're called the transition elements, okay? And here, the moat, they're called the inner transition elements. And the reason they're called the inner transition elements is if you actually drew the periodic table where you put these all in order, the periodic table would look something like this. So there's a tower. This would be there. This would be the moat. And then it would continue. Oops, I made a mistake. We'll call this this would be the rest of the inner transition elements. So this would be main, transition, transition, and inner transition elements. So you kind of expand the periodic table, and a lot of people call this the expanded periodic table. Now, the reason we don't draw it this way, I found out, I used to joke about this, but I found out it's actually the truth, is if you take a look at the expanded periodic table, it doesn't fit on an 8.5 by 11 sheet of paper very well. But when you take this moat out of the expanded periodic table and shove this together, you get something that fits on an 8.5 by 11 sheet of paper very, very much easier. So you should know those different ways of describing the periodic table. You should know the rows. You should know groups. You should know groups 1A through 8A. You should know where the main group elements are found, where the transition elements are found, and where the inner transition elements are found. Now, there's another way to divide the periodic table, and that's into what we call the metals, nonmetals, and metalloids. Now, before I tell you what is what on the periodic table, let's look at some characteristics of each of these. So metal, it's a solid at room temp, except for one metal, mercury. They're malleable and ductile. That means that when you strike them with a hammer, they will deform, they don't shatter. In fact, that's how they used to make coins. If you find an old Roman coin, often you'll find the head of some famous person in the middle of the coin, or kind of in the middle. It's supposed to be in the middle, but the way they used to make coins is they used to put a little slug on a if you will, a form that would make the shape of the face, and then you'd hammer it from the back side, also with something that would be on the coin. And when you hammer the slug, the metal slug, it would deform into the shape of the coin. Well, to get the face right in the middle of the coin, you'd have to hammer it right in the middle of the slug, which was rare. Not a very good job if you don't like swinging a hammer. Metals conduct heat and electricity. They are shiny, and mostly they are silvery. Those that aren't silvery usually are called out by their color. So copper is a color because of the element copper. Now, when we look at the comparison to nonmetals, most nonmetals are gas at room temp. There are some that are solid, at least one that's a solid, one that's a liquid, and actually a few that are solids, one that's a liquid. But most are gas at room temperature. If they are solid, they're brittle. They're non-conductive. They don't conduct heat or electricity, except for one form of one of the elements. They're dull if they're a solid. Charcoal is pure carbon, and that's definitely a dull color. And they're often colored. Charcoal is black. Now, here, when we look at metalloids, metalloids means kind of like a metal. Now, you'll notice it says that the properties are varied here. So let's take a look at one metalloid. And here are the metalloids on the periodic table. You start at boron, you go down as a diagonal, and it includes these two elements here. And you want to know which of the elements are metalloids. It includes silicon. Okay, so here is silicon. And silicon is a metalloid. So let me tell you some of the properties of silicon. It's a solid at room temp. It's brittle, like a nonmetal. Solid, like a metal. It doesn't conduct electricity very well. And it doesn't conduct heat very well, but it can. In fact, some people call it a semiconductor. So silicon is a semiconductor. All right, silicon is shiny and silicon is silver. So what I'm here to tell you about the properties of metalloids is that some of their properties may be like metals, some may be like nonmetals, and some may be in between. So if that's the case, we don't really have a set of properties that we can give to metalloids, because when you go to a different metalloid, its properties will be a little bit different. So let's just say that metalloids have some properties that may be like metals, some may be like nonmetals, and some may have a property where it's in between a metal and a nonmetal, like the semiconductor. Okay, so let's take a look at where these are on the periodic table. Once you know where the metalloids are, those elements to the right are nonmetals, including hydrogen to the left. That's the one that's off to the left. It's kind of weird. It turns out that hydrogen is also metallic. Scientists have recently discovered a form of hydrogen that is metallic, and it's of very great interest. It could open up whole new avenues of research. And all the elements to the left are metals. For us, we're going to consider hydrogen to be a non-metal, and you need to remember that, as well as where the rest of the metals are, the metalloids, and the non-metals. Okay, groups of interest on the periodic table that you want to know the names of and some of their properties. It's a very small portion of their properties. So one group of interest is group 1A. They're called the alkali metals. Now, of course, since we're calling them the metals, we're not going to include hydrogen because we consider hydrogen to be a nonmetal. These elements are highly reactive, and you can't find them as a pure element in nature. That's how reactive they are. Once they react, they become stable, and then you can find them. So you can't find pure sodium in nature, and that's an alkali metal. You can find sodium chloride, it's reacted, and sodium chloride is a stable substance, but it's not pure sodium. It's sodium combined chemically with chlorine. Okay, so they're called the alkali metals. 2A, they're called the alkaline earth metals, also highly reactive. You can't find them pure in nature. Now, for these two, they're so reactive that you can't find them pure in nature. Where can you find them pure? And that answer is simple: in a chemistry lab, where you make it react to become pure. All right, so you want to know those alkaline earth metals. Group 7A are called the halogens, also highly reactive, not found in their pure form in nature. And when pure, that is when they've been purified in a chemistry lab, the particles are diatomic. So there's F2, Cl2, Br2, and I2. You find them in pairs. Group 8A, they're called the noble gases. They're also called the rare gases, and they're called the inert gases. They're called rare gases because they are rare. They're called inert gases because they're unreactive. And as such, since they're unreactive, they're found as single atoms when you have a sample of it. Okay, so why noble gases? Well, if you think about rare and inert, inert means it doesn't react with other things. Well, nobility doesn't react with the peasants, right? And rare, nobility is rare compared to the peasants. So noble gases. They're rare and unreactive, gaseous at room temperature, and the particles are single atoms. Now we're going to jump to compounds. And specifically, we're going to be talking about molecules, compounds, and formulas. So here you want to recognize and interpret molecular formulas, condensed formulas, and structural formulas. You want to remember formulas and names of common molecular compounds, and you want to name and write formulas for binary molecular compounds. So let's get started. So for molecular compounds and formulas, very generally, compound is a pure substance with atoms of two or more elements with a specific ratio of atoms. There are two types of compounds. One is the covalent compound, where the atoms are held together by shared valence electrons, and there's the ionic compound, which has ions held together by charge attraction. We're going to be focusing on the covalent compounds, and then we'll switch to the ionic compounds. Okay, so let's look at the properties of covalent compounds. The atoms are held together by shared valence electrons. There's usually only nonmetal elements in the formula. And so now you know why it's important to know where the metals and nonmetals are on the periodic table. Looking at a periodic table, you can say, based on the formula and where they are on the periodic table, it must be a covalent compound. They have relatively low melting points and boiling points. To give you an idea of the low melting point, most of these you can melt in a pan on the stove top. So for instance, sugar can be melted on the stove top. It is definitely a covalent compound. Table salt cannot be melted in a pan on the stove top. It is not a covalent compound. So it's just kind of a rough idea of whether it would be a covalent compound or ionic compound. Can you melt it on a stove top? Yes, covalent. No, ionic. I'll give you another example. Wax. Can you melt that on a stovetop? You bet your bibby. What kind of compound? Molecular. Okay. Most are not water soluble, but some are. The smallest particle that has the properties of the whole is something called the molecule. The molecule has a specific ratio of atoms of elements. And so here I've given you an example of a molecule held together by covalent bonds. Those are the lines. And its formula is H2O2, okay? 2 atoms of hydrogen, 2 atoms of oxygen. If solid, they often have a crystalline structure, but no lattice. So a lattice structure is like a 2-dimensional lattice where you think of a lattice work that you use to maybe raise flowers or vines. Here we're talking about a three-dimensional lattice because of the way the atoms are arranged. Here there is no lattice, so there's no point in showing you the lattice. The formula is neutral. So when we talk about molecular compounds, the formula of the compound is neutral, which means when you look at this whole thing, the number of electrons equals the number of protons. We're continuing now. Actually, we're not going to continue with molecular compounds. In contrast to molecular compounds, we're going to look at properties of ionic compounds. So let's take a look here. I'm going to put that list back up, and we're going to see here we have the atoms are held together by shared valence electrons. Properties of ionic compounds, atoms are held together by charge attraction. So we learned about that in the past, that opposite charges are attracted. Well, ionic compounds, the atoms are held together by charge attraction because they're not atoms, they're atoms that are ions, okay? So here, it's usually a metal and a non-metal element, a relatively high melting point and boiling point, some water soluble, some not. Smallest unit is the formula unit, and the formula unit has the simplest ratio of atoms of elements, okay? It has a 3D crystalline structure. The formula is neutral. And I'm going to go back here where it says the smallest unit is the formula unit, and it's made of cation and anion. And just to give you an idea, the ion has a negative charge and the cation has a positive charge. So where we say the smallest unit of a molecular compound or covalent compound is the molecule, the smallest unit of ionic compound is a formula unit made of a cation and anion. This is an example of that two-dimensional crystal lattice that I was talking about. Now, how could this be three-dimensional? Well, let's talk about the two-dimensional first. Notice I have a sodium, then a chlorine. Opposites attract, so it makes sense to put those things with opposite charges next to each other. Now, you can see that this is a two-dimensional lattice. So if we look at this sodium, what would be the atom to the right of the sodium if we continued this lattice? And if you said chlorine, you're absolutely correct. Now, what if I were to put an atom in front of that sodium, what would it be? If you said chlorine, that would be correct. Now, I don't want to try and draw a chlorine in front. Maybe I can try and draw a chlorine back here like this, and a sodium back here like this, but you can get that three-dimensional lattice. And it's a crystalline structure with a 3D lattice. The formula is also neutral. So when you take a look at the comparison of properties of covalent compounds to properties of ionic compounds, if you know one list, you can bounce off of it and figure out what the other list is. I probably told you this before, but on exams, I often ask for a list of properties or a list of descriptions of particular things, and you should know those lists. Now, here we're going to focus on covalent compounds. So these are things that have molecules as their smallest ratio. So here, we're looking at formulas of these compounds. So this is called the molecular formula. The molecular formula is just a list of the elements and how many of each. So this C stands for carbon, the H for hydrogen, the O for oxygen, and the number following the element is how many of that particular element, how many atoms of that element. So there's 2 carbon atoms, 6 hydrogen atoms, and if there is no number, it's a 1. That's implied. So there's 1 oxygen atom. So that's the molecular formula of a molecule. Now, the structural formula shows how the atoms are bonded. Each one of these lines represents a covalent bond with 2 electrons in it. So this shows how all of these atoms here are combined together. Now, another way to show this is to show not only the bonding electrons, but the ones that are not bonding. So you see these little dots here on the oxygen? Those are electrons, but they're not bonding to other atoms. So these two look identical, except for the oxygen has lone pairs. We'll learn more about that in a later chapter. And then there's the condensed formula, which I call the typewriter formula. The formula you might have used back when there were no such things as computers and you wrote books with typewriters. So the way you start this formula is you don't start with one of these end atoms. You tend to start with one of these middle atoms, an atom that has other atoms bonded to it. And then you list all the atoms that are bonded to it that are basically dead ends. So if you start at this carbon and you go to this carbon, that's not a dead end. But if you go to this hydrogen, that is a dead end. And we have 3 dead ends here, so you put those 3 down next to it, CH3. You go to the next atom, carbon, so that's what we're going to start with. What are its dead ends? Well, this hydrogen and this hydrogen. This part of the molecule we've already taken care of, so we're not going to worry about it. So we put H2. And then here's the next one, H, and what is its dead end? H. So this is CH3, CH2OH. So these are formulas, all formulas that match this molecular formula. And here's one of the problems with molecular formulas. Sometimes there's more than one molecule for a molecular formula. Here is the same molecular formula, same ratio of atoms, and here's a different way of connecting them all together. But it has exactly 2 carbons, exactly 6 hydrogens, and exactly 1 oxygen. Here is the Lewis structure, and you'll notice that we have the lone pairs in there. You're not going to be responsible for this type of material on the exam, but it will be on a future exam. So this is, if you will, a trailer for the future. And then here's the condensed structure or formula for that. The one thing you should know from this slide, dead to rights, is molecular formula. If I ask you for the molecular formula of something, and I give you this or this or this or this, or any of these, and I ask you for the molecular formula, you'd better be able to count the atoms, figure out how many of each, and write out the molecular formula. You have to be able to do that. Okay, so for example, we look at this condensed formula. What is the molecular formula? Well, I see 2 carbons, C2. I see 3 plus 2 plus 1 hydrogens, H6, and I see 1 oxygen, O. And notice, usually for molecular formulas, you write them in alphabetical order. The elements, that is. The symbols are in alphabetical order. Okay, now, you do need to know how to name binary molecular compounds, and if given the name of a binary molecular compound, come up with a formula. So what is a binary molecular compound? Well, remember, we said that molecular compounds are compounds that usually have 2 nonmetals, okay? 2 or more nonmetals, I should say. Binary means exactly 2 types of elements, okay? There's a special way of naming things with hydrogen. We're going to skip that, and we're going to go with this way of naming all of these binary molecular compounds, okay? So, let's see what I wanted to get across here. Here we use prefixes. We also use elemide. And here are the elemide type names. We'll get into examples here in a little bit, so don't worry too much about the instructions here. But since these are all nonmetals, what I've done is I've given you all the nonmetals and I've given you the elemide part. Okay, so carbon becomes carbide, nitrogen, nitride, oxygen, oxide, fluorine, fluoride, phosphorus, phosphide, sulfur, sulfide, chlorine, chloride, and so forth. Okay. Now, when we're naming these, this is the way to look at this part right here. The first part of the name is the prefix plus the element that it is. The second part of the name is a prefix plus elemide. So let's look at an example down below. So imagine that we have CO. How do we name this? This first one is carbon. Now you'll notice this little star here that says, use the prefix if there's more than one. Well, there's only 1 carbon, so we don't use a prefix. Now the second element is oxygen, and this one says always use a prefix. So since there's 1 oxygen, we're going to call it monoxide. Now often when you have these prefixes plus the elemide together, if there's 2 often if there's two vowels in a row, you get rid of one of them. So this becomes carbon monoxide. Okay, so that's how you name these things. Let's take a look at some examples. But before we go to the examples, here are the prefixes that you need to memorize. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. You need to memorize those. Mono, di, tri, pretty easy. Tetra, maybe not as easy. Penta, you've probably heard of pentagon, 5-sided building. Hexa, you've probably heard of hexa somewhere before. Hepta, octa, nona, and deca, you've actually kind of heard of before, and they do kind of match what I call the months of the year: September, October, November, and December. So it turns out that in the past, about 2,000 years ago, there were only 10 months in the calendar. September was the 7th, hepta, September. October was the 8th month, octa, October. Nona was the 9th month, or November was the 9th month, nona, and December was the 10th month. And it actually makes sense because we know that an octopus has 8 tentacles, right? And yet October now is the 10th month of the year, and that seems a little confusing. But octa, or octo, means 8. So October used to be the 8th month of the year. If you want to know what months were added to the calendar, they were January and February. And the story is that about 2,000 years ago, there used to be this time called winter. And it was an indeterminate amount of time. So fall would end and winter would start. When would winter end? And the answer would be when someone damn well pleased and said, you know what, winter's over, spring's starting. And then they decided, you know what, we need to be a little more consistent about the calendar. We need to have a winter, and let's go ahead and add 2 months to it. And that became January and February. Okay, so that's how I remember 7, because it's like September, hepta, 8, October, octa, November, 9, nona, and December, 10. Because December does sound like deca, right? And we know decade is 10. Okay, memorize those prefixes. And here we have a bunch of examples. And here you'll notice we have the skip, and we're going to do this instead. So that means that, just to remind you, I'm going to write the rules down again. The first element, we use element, and the prefix, if more than one. And the second element, we use prefix elemide. So if we take a look at HF, HF becomes hydrogen monofluoride. No prefix for the hydrogen because there's only one hydrogen. Water, H2O, becomes dihydrogen monoxide, one of the most dangerous chemicals in the world. H2S, dihydrogen monosulfide. Now, do you remember how we said that elements in the same group have similar properties? Well, oxygen and sulfur are in the same group. Look at how many hydrogens they combine with. They both combine with 2 hydrogens, so that's a similar property. Here are some more examples. NF3 is nitrogen trifluoride. NO is nitrogen monoxide. NO2 is nitrogen dioxide. Here's where we're going to keep both vowels, because if we don't, then it becomes nitrogen doxide or nitrogen dioxide. Dioxide sounds just fine. N2O is dinitrogen monoxide, and S2F10 is disulfur decafluoride. So you're wondering, why aren't there more examples with a whole bunch of elements in the front here? And the answer is because they're uncommon. Okay, so those are examples of binary molecular compounds. Likewise, if I were to cover up the formula and gave you the name, you should be able to come up with the formula. So if we look at disulfur decafluoride, you should know that that's S2F10. Good. All right, so that's the end of this lecture. We'll continue on next time with ionic compounds.